Activation function in deep neural network, the intuition behind. Let's go over the preview of this video. The visual explanation of why we need activation or non-linearity, and it's a theoretical derivation, but it's simple and easy to understand. It's a backpropagation algorithm and why we need non-linearity or activation function. With that, let's go into the video. Deep neural network is nothing but a spider web. No, it's not. It's a group of neurons connected with each other. Let's consider an example. Classification. This is cat, which is dog, which is ice cream. Sorry, ice cream. For simplicity, I'm just going to include cat and the dog, not you. So when we draw a line that separates cat, which is the dog, we cannot fit the data that well. It still has false positives and false negatives. But if we introduce non-linearity, and if we draw a line that is not linear but like curvy, we can capture a lot of true positives and true negatives and eliminate false positives and false negatives. That is where the non-linearity comes into place. Now let's go over the backpropagation algorithm. Here, this is layer 1 of neuron, layer 2 of neurons, layer 3 of neurons, and the fourth and final output layer. Each neuron is linear by default, and if we do not introduce non-linearity, let's see what will happen. We will derive the backpropagation equation in order to understand why we need activation functions. Let's start from L4 layer. The L4 layer is made up of a weight and bias. Weight W4 X plus a bias B. L4 is equal to. And this X is coming from the layer 3. The input into the L4, which is input into the L4. So X3 is equal to, it has 3 neurons. So each neuron will be like 3, 1, X plus W32 X plus W33 X plus a bias. Again, this X is coming from L2 input. So let's consider that as 2. We can rewrite this equation as W31 plus W32 plus W33 into X plus B. When we substitute that in our L4, I'll just substitute it here. W4 into X, this is 2 and this is 3, plus a bias. There is one more bias, but let's assume since it's just a number, any bias is just a bias. And even here, this will be substituted by a constant number, let's say 2, 3, 4, some random number, let's say 2 again. Then this again will be a constant number. We can consider that as W 4, 1, for example, and then X2 plus B, which is again a linear function. The linear function is usually be a linear line, right? And what we are looking for is not just a line. We need a curvy structure, which we cannot achieve just using just the neurons. We need some activation function to make into a curvy structure. For each neuron, we need one more layer. Once weight and biases are calculated, this is passed into our function, that is activation function, which is either sigmoid, Relu, or different activation ALU, or different activation functions you want. If you use the activation function in each neuron, then the shape will be converted into something like this, or this, and then it will be converted into that, and then somewhat is combined together to form the perfect shape that you're looking for. Initially, it used to be linear, but everything is converted into the shape that you want, and now you can classify it like this, which will give you a perfect score. And even ice cream is happy. Then you may have one question. Why do we consider Relu as a nonlinear function? The Relu has a shape of a linear, that is a line, and one more line. That's the reason it is considered as a nonlinear function. If it's just a single line, we cannot fit the data well. But let's say if it's two lines, we can somewhat fit the data. And let's say if we have like a multiple neurons with full of Relu function, then we can get some shape like that, and that will fit your data really well. That's why even Relu is considered as a nonlinear function. Thanks for watching. Ice cream is so happy. Please like and subscribe to my channel. Thank you.